All right, today we are taking a journey way back in time, diving deep into the silicon heart of a true legend, the Commodore 64. We're going to peel back the layers and see the absolute genius of 8-bit programming and how developers pulled off what really feels like magic, given the incredible limitations they were working with. So, right off the bat, you're hit with this massive puzzle. Over on the left, you've got the processor's brain, its registers, and they can only hold a number up to 255. That's it. But on the right, you have this sprawling 64 kilobytes of memory. That's over 65,000 different locations. So how on earth does a brain that small command a body that big? This was the fundamental problem C64 programmers had to solve every single day. And that's really the first part of our story. To get around this 8-bit barrier, the engineers and programmers came up with some unbelievably clever workarounds. See? They couldn't just build a bigger brain for the chip, so they taught the one they had how to see that entire memory map using some brilliant software tricks. And that trick, it has a name: advanced indexing. The idea isn't to have one register somehow hold a giant address. Nope. Instead, it's a technique that kind of stitches together smaller 8-bit pieces, like the processor's own registers and pointers stored in memory, to build or forge a complete 16-bit address. This is the absolute key that unlocks the machine's full potential. Okay, so how did this actually work in practice? Well, there were two main ways to do it. With what's called pre-indexed addressing, you take a base address and add the value from the X register before you looked up the final address. With post-indexed addressing, it's the other way around. You first grab a 2-byte pointer from memory, and then you add the Y register to it. You know, two different paths, but they both get you to the exact same place: a precise 16-bit location anywhere in that massive 64 KB map. Okay, so problem 1, solved. We can now point to any memory location we want. But of course, that just opens up the next big challenge. If the machine can't even count past 255, how in the world does it do complex math with much, much larger numbers? The answer lies in this one tiny single bit tucked away in the processor's status register. It's called the carry flag. And honestly, it's the unsung hero of all 8-bit math. When you're adding numbers, it acts like an overflow valve, catching anything that spills over 255. And when you're subtracting, it becomes a borrow bank, letting you borrow from the next column, just like you did on paper back in school. Let's watch it work with addition. Before you even start, you have to run a command called CLC, which stands for clear carry. That makes sure your overflow valve is closed, set to 0. Now, let's say you add 5 and 249. You get 254. Fits just fine, no problem. But what if you add 20 and 250? The answer is 270. That's too big. So the accumulator keeps what it can hold, which is 14, and that little carry flag flips to 1, holding on to that overflow. You can then add that carried 1 to the next byte in your calculation, letting you chain these things together to work with huge numbers. And subtraction is just as brilliant, maybe even more so. With this, you start with the command sec, or sect carry. Think of this as pre-approving a loan from your borrow bank. In step 1, you subtract the lower bytes of your numbers. If you need to borrow, that carry flag flips from a 1 to a 0. It's like a little borrow thread that signals to step 2, telling it, hey, when you subtract the upper bytes, you also need to subtract an extra 1 that we loaned out. It's an incredibly elegant system. Okay, so let's recap. We can get to any memory we want, and we can do math with big numbers. The final piece of this puzzle is, how do we teach the machine to make decisions? How does it know when it should jump to a different part of the code or when to repeat a loop? And that's where comparison commands come in. Something like CMP, or compare, doesn't actually change any of your data. Think of these as the program's senses. It performs what you could call a phantom subtraction. It compares a value in a register to another value, and then it just flips a few physical switches or flags based on what it found. If the values were equal, the 0 flag gets set. If the register's value was smaller, the negative flag gets set. And this is how you build actual logic. After a comparison sets those flags, the branch commands read them. And just look at the efficiency here. A long, wordy, basic command like if a equals 0, then go to, boils down to a single 3-letter instruction in assembly, BEQ, or branch of equal. The code isn't just shorter, it's running directly on the metal, reacting instantly to the state of those little physical switches. And when you put it all together, you get this. The master cycle, the absolute heartbeat of the machine. Step 1, locate the data using indexing. Step 2, process it using math and logic. Step 3, update the status flags based on the result. And Step 4, redirect the program using control flow that reads those flags. Understanding this loop is everything. You're not just sending suggestions to an interpreter anymore. At this level, you are physically driving the silicon. So we've gone through the theory, we've seen how assembly works around the machine's physical limits. Now let's see the truly staggering, real-world impact of all this in a final showdown: basic versus assembly. Let's just look at the raw numbers for a super simple task: filling the screen with a single character. The basic program needs 41 bytes of memory. The assembly program, just 25. But that's not the amazing part, the execution time. That's the real story. In BASIC, it takes over 5 seconds. It's slow. In assembly, it is literally instantaneous. And that's what this shows so perfectly. The difference isn't just about numbers on a page. It's the difference between watching that slow, chugging progress bar and feeling the snap of an instant result. For games, for applications, for pretty much everything on the C64, this absolute domination in speed and efficiency was the ultimate prize for mastering the complexities of assembly. So why does any of this matter today? Well, because assembly programming gives you direct, unfiltered control over the hardware. It lets you overcome physical limitations, like that 8-bit brand in a 16-bit world, through nothing but pure, elegant software. And it was exactly that ruthless efficiency that made all of the fast, responsive, legendary games and applications of the 8-bit era even possible. And, it leaves us with a final thought. We live in an age of basically infinite computing power now, where we can afford to be messy and wasteful with our code. But when you look back at the C64, you really have to ask, in gaining all this power, what have we lost from that era of truly elegant, beautiful, and efficient code? It's something to think about. Thanks for joining me.